Everybody tells us quantum computers are coming. Already DOA has marketed quantum computers, sold it to DARPA, sold it to Airbus and Boeing or some other companies. So, and they are using quantum annealing process by which you have a potential, you set a potential, and you go to the global minima faster by tunneling through different energy minimas. But energy minimization is not a universal computing. You have to rewrite the problem in so much complexity so that eventually, if you solve the energy minimization problem, your other problem gets solved. So that is the problem with universal computing. And what is universal computing? We should always keep it in mind that whatever the function you are doing, suppose I have a pen that transforms into a bottle. Okay, so if pen transforms into a bottle, if that is a function, then this function, if I apply on another time, I mean, then this transformation will be valid in global scenario. It means, suppose I have a tape and it works like a typewriter, tick 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 tick. That machine you can simulate in another machine. It's a hard machine, and that machine can simulate all this kind of Turing tick 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 writing or universal. So then it becomes universal system. So basically a machine A, if it can be emulated by another machine, that is A dash, who can do all kind of A's different variations, and whatever you do you can get it done over there. Then it becomes universal computing, and that's the problem is not doing one particular task very well, but a lot of other tasks very well. So today we will dive into why quantum computer is not possible, is not going to come anytime soon, a proper quantum computer. The reason is the following. To make a quantum computer, what are you doing? You take a classical computer and create all kind of analog systems, replica of every single component that you have in your classical computer, make a quantum analog, and you are doing it. Logic based computing, there are many large number of adiabatic computing. You have continuous variable, CB, DB, discrete variable computing. So where you could do 0, 1, 0, 1, or you can take phase, continuous values. Whatever you do, doesn't matter. What is the problem you want to solve? And does that problem solving requires quantum phenomenon? And what a quantum phenomenon are you using? All the quantum computers that exist in the world and being designed, being planned, and being researched, and investment are coming. All quantum computers have only one thing in common. They want to solve exactly the problem the classical computer solves. And those problems, they will solve faster with minimum number of resources. This is a big hype and overestimation, because under any circumstances you cannot use less number of resources to do similar kind of computing. The reason is the following. Suppose to solve a problem you need 1000 bits, and you have to write it with 1000 qubit. If you don't write with 1000 qubit, what does that mean? That means one qubit has two classical channels, and it's a block sphere. So infinitely possible options are there between 0 and 1. And on this surface, there are some localized regions following a particular kind of symmetry, and you access them. So amount of resources that you need to put through, if you take just the classical bits, you get only two output. I mean, it doesn't matter how many infinite possible states are there or not. If you want to really address those regions on the surface of the block sphere, and you want to take it for your purpose of computing, then you need enormous amount of resources to control and precisely take those superposition states. That people don't tell. That's why people say we're using one qubit, we will be able to solve all the problems of the universe. Yeah, 12 qubit is enough. If you want to do it, you would need billions and trillions of years. They are actually cheating and doing a fraud. The honest person, in building a quantum technology would say that, okay, if you need 1,000 qubit, I can give also. If you need 100 bits, I will use 100 qubit. Then the comparison begins. So resources are same and same. So the classical channels that you are getting the output is fine. Now you are correlating 100 qubits in a very different way, so that you can identify and get the resolution and get the output. But if you don't do this, then that's a problem. Now another problem, the major problem for which I am making this video, is that they always tell you that they will do it faster. It has been shown by Juska and Rape and several others in 2008, 2009, 2010. Series of research articles are published that if you do factorization, only then you will get advancement. If you don't do factorization, then you will not get any advantage. Because if you need to break the entanglement, get the output, and then take it to the next step, you will have to compromise. So the people have come up with modular quantum computing. Many quantum computers are there doing little tasks, and you integrate them in a larger manner. Then again, you are losing the resources, advantage of resources that you are supposed to get. Or people tried with many different ideas that we will create many idler state, and that is also another fancy thing that they talk about. That, okay, I am one signal is coming, I split it into 100 channels. I divide into, because 1 million photons are creating a quantum, say quantum light, or a coherent beam of electron. I split it into 100 different parts. Everywhere it is psi, okay, up to 100. Now, if you have detectors, all polarization are little shifted in all the detectors, and you want to find out how the wave function looks like, because quantum computing is all about, eventually you have to tell what is the wave function looks like. They use a fancy word called Wagner function or quantum tomography. Simple thing is how the wave function looks like, and how the wave function looks like means each and every pixel you have to read. So if it is a 1024 qubit quantum computer, then 32 by 32 pixel you will only get. So 32 by 32, that means 1024 different kind of sensors are there, and coincidence counter is outside, who will check that you have arrived at the same time or not. Now all these sensors which are little twisted, they are considered as a classical channel. That's where they fool you. Now imagine this quantum light, or quantum signal, which after computation, when it goes to different 1024 channels, all the channel sensors, if it is they simultaneously detect, then all the sensors together will work like a quantum operator, and they will apply that operator will be applied on the actual density function or Wagner function that is coming, and then it will transform them together. Instead, what you can say that, look, I am changing it like this, but when quantum source is divided into and goes to individual channels, they forgot who they were. Now they give the independently the value, the measurement is done. This is where, when people campaign that they are measuring the density function, they are basically doing a dishonest act. Either they don't understand or they're doing something dishonest, because all the sensors will collectively transform it, and you will measure something different, as far as Wagner function is concerned. So you have to come up. I don't know. I'm not saying that I have the solution, but somebody has to come up, arranging the sensors in such a way that after this operator, this measurement, the whole Wagner function becomes invariant. That means psi into the operator is equal to psi. So even after doing the measurement, you get the data, but psi doesn't change and it doesn't become a new one. Then otherwise you can never do the measurement. So sensor wise, a big hype is given. Resource wise, a big hype is given. Now problem wise, if you have common problems, you can't. So what is the solution out there? So while building quantum computer, we came up with one thing that might help all of you. If you are thinking about quantum computer, building quantum computer, interested in quantum technology or quantum research, in, say, share market, say, internet cybersecurity data, or genetic data, which is rapidly changing. And your body, suppose you synthesize millions of different kind of molecules. So sometimes you are continuously attacked by antigens, and antibodies produced. Antibodies production means the immunity system analyzes what molecules need to be synthesized, then synthesizes it and goes and kills it. So you can understand the enormous level of complexity, and every time it could be a completely new different molecules. Imagine how much time does it take for a drug discovery company to go there and find and discover and invent a new drug. Now you have to do this, you do it every moment in your body. And share market, when Donald Trump threatens something, and then whole share market goes up. Where is the variable? See, this is a beautiful situation where quantum entanglement, quantum superposition, and in quantum, there is no motion, there is no energy supply. So one object wants to go A to B, will disappear from one and will reappear in B. It is not they will walk. So quantum walk and other concepts, they say it is walk, but inherently they do consider that the particle exists in all the destinations of the path at the same time with a different probability. So there is no physical walk happening. The particle reaches at the destination with some probability even before the walk begins. So that's why don't get confused with quantum walk. Now coming back, so if you have a real world scenario where several variables are there in the share market, who, if you change one, all others change in a very different way. But say 5 of them are making a group. If you change A, all 4 changes in a certain way. But if you change B, they also change in a completely different function. No relationship. When you have this kind of situation, this is non-algorithmic. You cannot frame any algorithm for this kind of situation. Entanglement. Suppose 2 different variables are there. Economy of a country and whether it is engaged into war or not. They are connected together as a collective piece, and that controls the share market ups and downs. So if you have this kind of scenario, if you change one, other variable disappears. Any other variable. So it's kind of a entanglement like scenario. If you have this kind of situation, non-algorithmic. So you need to find out where rapidly changing data is there. A non-algorithmic scenario, if you are finding algorithmic like periodic events, something happens repeatedly in repeated time, that's logic. If there is a cause and there is an effect, if this cause happens, always the effect will be like that. That's a causal thing. And that's why fidelity, when people claim that they have 100% fidelity, they are making you fool. Think about it. When you have superposition of many of them and you have a conditional fixed relationship, then how are you doing it? So fidelity 100%, 99.99999% is kind of making you fool. It's a classical measurement. Just like the way people do tomography and determine the wave function. So the problem that is happening around us in nature, that resembles quantum-like phenomena, which cannot be explained with any logic. But quantum-like situation happens, you can create on-demand quantum circuit that can replicate those scenarios and can give you an integrated controlling mechanism which can generate possibly those kind of scenarios. So those problems where you cannot create a scientific model because of the randomly changing rapid data, quantum computer can give an insight into that. So our quantum computer, the way we are making it, is trying to solve this particular scenario where we can get actual use case. Currently, Google is very right. They have started XPRIZE because there is no use case. Practically, there is none. Then what is happening with the billions of dollars investment? Because they are making a practical replica of the classical computer. To get a use case, first hype and hiding parts where dishonesty is hidden and overestimation is there, that has to go. No measurement, no simultaneous measurement can safeguard you. If you have simultaneously many sensors, you are creating an operator, you will transform the whole that is coming input as a collective response. And you need to do some real research over there to resolve that problem. You need to find out how you can create multiple quantum channels operating simultaneously to solve the error. If you allow in your quantum circuit quantum error to be born, simple calculation can show you that cost will be so much that after a certain level you cannot, your cost will be something like cost for qubit is like this, and cost for quantum error correction exponentially would increase. You can't do it. So all these huge problems are there, which we hide. We do not mention, we do not try to resolve them. Instead, we just go on claiming, oh, you have created 50 qubit. Okay, I have created 100 qubit. You have created 250 qubit. I have created 1000 qubit. Come on. Even if you do 1 million measurements with your sensors, SPRE and coincidence counters and something, your resolution never increases to determine the wave function, that you want to measure after computation. Never. But many research papers continuously claim this kind of thing. So today I will end this suggesting that the hype of quantum computer is almost like molecular electronics, which say that single molecule will do every single electronics and the world will change. The carbon nanotube hype, when they say the carbon nanotube is based nano radio, and so many different things have been created. So the hype will come one after another. Graphene, it was told that every single thing you will come with the graphene. And people are dying now to make a real use case. And they are doing something because people are desperate to use it for some use case. Instead, if we are little honest, organic solar cell, I started my PhD 25 years back with organic solar cell. I know how they lie in the research paper. They don't tell the truth, and then they publish Nature, Science, and top journals of the world, and that destroyed researchers like us when we are doing the PhDs. So I hope that my discussion has helped you to understand a little bit that what is going wrong with the quantum computer research and where we should concentrate and do some work, try to do some work. Even if we fail, doesn't matter, but we should try to do some work over there.